In this task, students would explore the Finsler-Hadwiger theorem. In geometry, I used to devote a day each unit to explore theorems that we wouldn't actually be studying in class. They're more obscure theorems, but they allow for deeper understanding and thought, and it gives students an opportunity to build those deeper connections with geometry. This theorem, for example, states that suppose that you have quadrilateral A, B, C, D, and you have A, B dash, C dash, D dash. So why the A is the same? Because they have a common vertex A. Let E and G be the midpoints of B dash and D dash and B respectively, and let F and H be the centers of the two squares. So the last statement, which isn't on that text right there, is that quadrilateral EFGH is a square. So I provide students without that because I want them to make the conclusion. So they know that they can draw any extra segments, anything more that they think that they can then pull from a conclusion from. So as students are working through recreating the theorem, I am a little bit more involved in making sure that they, at least before they draw the conclusion, that they see what they're trying to create here. So I'm going to run through what they're supposed to do here. So with GeoGebra, you can make a regular polygon by selecting that, and then if I want it to be a square, then I will make my 4 vertices. I'll just move this a little bit. And then, so that's my triangle A, B, C, D. So I know that they want to share A. So I'm going to turn this a little bit so that they can share A. And then I'm going to make my second regular polygon, but remember I'm using A again. So I want 4. And then, And then I need to move this a little bit out of the way. So when students are doing this, a lot of times I walk around and I see that they try and make them the same size. But I do want my students to always show me different cases. So ultimately they end up like making one really small like this, or they make it closer together, different things. So I'll just kind of do mine like this. And then I'm really particular about, I like when my students rename how it's supposed to be in the theorem, so that we all kind of are on the same page when they show their reports with one another. So I'm going to go through and do that really quick. Oh, sorry. Okay. Oh, made a mistake. Sorry, I'm so used to doing this on Windows, and now I'm on my Mac, so it's like just a little bit finicky. Okay, so we're going to let E and G be the midpoints of BD, so right here, and then over here. So, I guess that's typed wrong. Okay, I'll have to fix that. So when they make the midpoint, they can go ahead and find midpoint, if I'm not losing my mind here. Okay. Midpoint. So I'll have some students do it like this, and then I'll have other students actually create a segment, and then they go ahead and they find the midpoint of that segment. So depending how they approach this kind of then leads into how they find their conclusion. So ultimately, it's good for students to draw this segment, because that's going to lead into the next part here. And then it says, let F and H be the centers of the two squares. So at this point, they kind of run into, okay, where is there going to be a square? So I have students that start to connect segments, which ultimately this is what I want them to connect. And then by finding the midpoint of this segment here and this segment here, which they're allowed to do, they're allowed to find any midpoints or find any angles or side lengths if they want. They can draw extra lines, anything like that. But what they're going to discover is that then by connecting all of these midpoints, they then have a square. So a couple things that they would then do to kind of prove to me would be that they would be able to find the distance of all the sides. So once my students would see that, they would say, oh, well, now I have a square. Obviously, this right now could be a rhombus. So next, they would want to find the angles. So then they could show that all of these are 90. Really, you could just show 2, but we'll just put them all in. And so that would be the conclusion that would come from this theorem. So one thing that's cool is it does take a full 90 minutes for them to do these things, but it's neat because so many different people, they have like different lines here, or maybe somebody made a circle, and I don't remember specifically with this one, but a lot of times they will then kind of they'll answer this theorem and then they'll discover like partial of another theorem. So a lot of times with these mathematicians, they created theorems and then they used that theorem, which, I mean, we all know as math teachers, to then create something else. So I've seen students that start to discover other theorems within the theorem that they're supposed to be investigating. So in this specific activity, I do believe it creates those mathematical habits of mind. For reasoning and relationships, students would see how the properties of this two-dimensional polygon, the square, has relationships to create other squares. They'll be able to make relationships by showing the different cases. So sometimes my smarter students, they'll show different cases by just moving it but not restarting. And they'll just kind of play around with it. Sometimes I do have students that will, they'll restart the whole thing. But it's kind of cool because, I mean, even as you bring the square inside, I mean, it's cool that they can just kind of play around and really see what they're being shown here. So that's for reasoning with relationships. I also think that there's a lot of generalizing geometric ideas that come into play when students are working on the other cases and discovering if the theorem holds true all the time and then maybe when it would not work. So sometimes, depending when the students complete the task, they could try it with just maybe rectangles or trapezoids or different quadrilaterals and see if they can build a similar relationship. And then there's always balancing exploration and reflections, I think, in a lot of these geometric technology tasks, because students have to draw their own conclusions from the theorem that I provided them. And then they always, they create their own questions when they're doing self-discovery. So for example, they could ask, okay, what did this provide me? What is this going to help me to understand? How would this work with other polygons, like I mentioned before? And then also students always kind of realize with all different tasks with GeoGebra, and even I have when doing some of the things in this course is, okay, what did I do that was extra here? Is there stuff that, okay, yeah, maybe it helped me get to my solution, but I can realize I didn't really need that. So that kind of helps them realize, okay, the things that I have here provided me with knowing X, Y, and Z, so whatever that is. So I hope that you guys enjoyed this. If you want to know some of the other theorems that I've had students toy around with, I could let you know. But it's just fun, and it's a nice relaxing day to just realize, okay, what are our properties of the square, for example? I mean, they have to still know that the opposite sides are congruent and that the angles are all 90 degrees. So even though it may seem like a confusing theorem, they're using things that they know that's just in 10th grade geometry. So maybe even it could be done in the 8th grade. I'm not sure. Maybe if you provided them more information in the theorem. But yeah, so I think it's pretty fun. So I hope you guys enjoyed. Thanks.